you guys in presenting some of the solutions. So I've put up the lesson plan as usual. For question 1, I'd like to ask for William's help. Vijay, if you could come join us. So let's look at question number 1. So question number 1 is about the cardinality of sets. It's about infinite sets, right? And the first part, so okay, so William is here. Please come. All right. So William had a partial interesting solution to the first part. So the first part basically asks, let us see this. So it asks us to show that a countable union of countable sets is countable. Okay. What does a countable union of countable sets means? It means like if you have sets S1, S2, S3 and so on, each set itself is countable and the number of sets here is countable. That is, there are as many sets as there are integers. Okay, or no more than that. So to prove that the union of these sets, if I take the union of all of these elements, to prove that this is countable, and notice that this is a non-trivial question, because if you look at question number D, so here if you're looking at a power set of all the natural numbers, and here we want to show that this set is in fact uncountable, right? Because the power set is a subset of integers. So every set within the power set is countable, but the number of elements in the power set is actually uncountable. So so to show so if you do something like this, then you can get something larger than a countable set. You can get something that is uncountable. You can get the set of all real numbers. Okay. So question number A does ask you to prove something non-trivial, something hard. Okay. And Vijay's first attempt was to try to do it inductively. So basically to show, okay, so suppose you have two countable sets, C1 and C2. So C1 is countable, C2 is countable, so their union should be countable. Okay, and what did he do? He basically mapped the C1 to the set of odd integers, C2 to the set of even integers, and therefore C1 and C2 themselves can be viewed as subsets of the set of all integers. Therefore, their union is going to be countable. Like that was the crux of his proof, right? So so let's remind ourselves again. If you want to show that there's a bijection between two sets, well, okay. So suppose you have C1 which is countable, C2 which is countable, and then here you have the set of integers. So this is the set of all possible integers, and let's say here you have odd integers, here you have even integers. So from C1, since C1 is countable, if you can do a mapping from C1 to odd integers, from C2 to even integers, then oh, this is not fully. Okay. Hopefully they'll get this to stop, but let me just keep persevering. So if you can do a one-to-one mapping from C1 to odd, C2 to even, then since these do not intersect, so there will be a one-to-one mapping from the union of C1 and C2 to the set of all integers, right? That's the basic idea. Oh, let me switch off the light here so you can see it a little bit better. Okay, so that was the basic idea. And if you look at the details of his proof, this is correct. This is basically just saying, you know, map the ith element of C1 to, or the nth element of C1 to 2n plus 1, nth element of C2 to 2n. So so therefore it's doable. You can do this. But the problem is, just because a finite union of countable sets is countable, that doesn't mean a countable union of countable sets is countable, right? Because again, we have to be careful when dealing with infinities. So you have to, you really do have to be careful. So my hint for this one was to use a Cantor diagonal type argument. Okay, and what do I mean by that? Actually, Vijay, I suggested this. Do you have any thoughts, William?
Still can also do target.
Okay, fine. So still having some trouble. So let's see how to do this one. And this idea is quite useful. So let's think about this. This is actually quite similar to what we did to show that there's a mapping between rational numbers and integers, right? If you remember, how did we do that? We drew a grid and then we drew sort of a diagonal line and then we did that mapping, right? So we'll do a similar thing here. So suppose someone gives us a countable sets of countable union or a countable number of countable sets. So let's put them along this axis. So S1, S2 all the way till Sn, and then further on dot dot dot. So this is a potentially infinite number of sets, and every element here. So the element of S1 is maybe A11, A12 dot 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 till A1n, and then dot 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 like this. And similarly here we have A21, A22 dot 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 A2n dot dot dot, right? So every set itself is potentially infinite, but it is also countable. So we have something like this. So now if we want to take a countable union, so if we want to take the union of all of these sets, we want to take a union of all of these sets, what do we want to do? We want to show that we can assign so for the union of SIs, we should be able to show a bijection. We should be able to show a bijection between the set of natural numbers and this set over here. Okay, so or to show well, okay, not necessarily a bijection, because these sets themselves may be finite. These sets may be finite. So in that case, it may be a subset of the set of natural numbers, right? And if it's a subset of the set of natural numbers, then that's fine. Then that's certainly countable. Union of finite sets is going to be countable. The trouble happens when each of these is infinite. So if each of these is infinite, we want to show that this thing is a subset of the set of natural numbers. That is to say, we want to assign every element here to an integer, and then we will show that these unions can be the union of this the countable union of these countable sets is in some sense a subset of the set of natural numbers. So how would you do it? Well, you just use the same trick that we did for the integers. So that is to say, you the first element in the first element you map to 1. The second element here along this line you map to 2. The third element along this line you map to 3. The fourth element along this line you map to 4, 5, 6, and so on. Okay. So via this process, if you think about it, any element in any set is eventually going to be assigned an integer, right? And every element will be assigned a distinct integer. Therefore, there are at least as many integers as there are elements in the unions of these sets, right? Therefore, a countable union of these countable sets is still countable. That is, we can assign integers to them, right? That's it. That's the trick over here. Okay, William, do you understand? Okay. Now this is a subtle point. It's a subtle point. So could you try to repeat for the class two things? Firstly, while your proof was correct, it was incomplete, right? I mean, it's important to also learn from mistakes. So point out the incompleteness here. And secondly, what we did in this trick over here. Okay. All right.
就是 Part A 这块，我只证明了2个可数集合的并集仍然是一个可数集，但是它这里要证的是可数集格个可数集的并集，它还是可数集，所以我这个证明是不充分的。然后老师刚才做的就是一个构造一个可数集合个可数集合的并集到自然数集的一个单设的一个函数，就是那个用线画的那个。
Okay. So you already talked about this as well, right? Okay, fine. So in this method, as he just said, you can take you can assign an integer to every element in every set, a distinct integer to every element in every set, and therefore it is this countable union is still going to be mappable to the integers, and therefore it will be countable. Okay. Now there are 3 other parts to this question, each of which is important, but before we do that, okay, fine. So let's keep this proof in mind, and we'll see in part D a very different result, right? In part D, when we take the power set of the integers, we'll get an uncountable set. So keep that in mind. Okay. The second question, for which Vejia had a nice solution, was asking us to show that the positive real axis has the same cardinality as the open line segment 0 to 1 by finding a bijection. So by finding a 1-to-1 map between them. And in this case, the solution that he used was, so he used f of x is equal to x over 1 minus x. So if you look at this, given any number between 0 and 1, it gets mapped to some number on the real line. Okay, so any number between 0 and 1 is certainly a number on the positive real axis. And given any number on the positive real axis, if you do f of x is equal to x over 1 minus x, then it gets mapped to the interval 0 and from 0 to 1, right? So this shows that again, the cardinality of these two sets is the same, right? Because you can have a 1-to-1 mapping from the line segment to the full half line, and from the half line back to the line segment. So therefore, these two sets have the same cardinality, right? Let me also do his solution to part C. Then I'll ask him to repeat that, and then we'll do part D. Okay. So part C asks us to show. Now this one is maybe a little bit more surprising. This asks us to show that the line segment 0 to 1 has the same cardinality as the square 0, 1 to 0, 1, right? Now the square is two-dimensional. The line segment is just one-dimensional. So how are these two sets the same? And the point is, both of these are infinite sets. So in fact, it is possible to find such a bijection, right? And that's basically what Vejia did over here. So he said, okay, so firstly, the line segment from 0 to 1 to 0 to 1 square. So the line segment is a part of that square. So certainly, you can find a mapping, you can find a 1-to-1 mapping from the line segment to the square. The trickier part is to find a 1-to-1 mapping from the square to the line segment, right? To find a 1-to-1 mapping from the square to the line segment. So suppose someone gives you a pair of real numbers, T1, T2. So suppose someone gives you, So suppose someone gives you a point in the square which is a comma b. So let's write a comma b, for example, in decimal format, right? 0.a1, a2 up till ak. This might be a terminating decimal. It might be a finite decimal if it's a rational number, or it may be or even if it's a rational number, it may be infinite, right? Either way, it's okay. But so it's either finite or infinite. But regardless, so what do? You find a real number where you interleave the decimal digits of these two real numbers. So A is the x coordinate, B is the y coordinate, and you take the first digit of the x coordinate, the first digit of the y coordinate, the second digit of the x coordinate, the second digit of the y coordinate, and you create this new real number, which will again be between 0 and 1, right? Because you started off with something between 0 and 1. So this new thing will be between 0 and 1. And for every distinct pair of real numbers, a comma b, you'll end up with a distinct real number, a1, a2, b1, b2, a1, b1, a2, b2, blah, blah, blah over here, right? So this shows an injection, that is a 1-to-1 mapping from the square to the line segment, right? So that actually shows that even these two-dimensional objects are actually have the same cardinality as this one-dimensional object, right? This is what happens when one works with surprising objects like infinite sets, right? Infinite sets, you have to be careful when you're checking the cardinality, whether one set is larger than the other or not, okay? And if some of you ever study, for example, measure theory, then you'll understand, or a more detailed, advanced graduate class in probability theory, then you'll understand these things at a deeper level. But right now, we're just introducing you to these concepts. Okay, so wait here, two things to be summarized here: parts B and C. So for part B, you use a description over here to show the mapping both ways, and then for part C, like highlight the fact that again the reverse mapping is the trickier one and how you did it. Okay.
就是 B 的话比较直观一点，你只要找到一个函数，然后定义域是在0到1里面，它既是一个满设到这个 R plus 这个区间，它既是一个满设又是一个单设，然后就想一下这样子把它塞进去就可以，然后那个上面写的那个就可以满足。然后 C 的话，我这里用了一个定理，就是如果两个集合，你可以从 A 找到一个单设到 B， 并且从 B 找到一个单设到 A 的话，那就说明它们是 of cardinality equal 的。然后从0到1半开半闭区间到0到1的平方这个区间是比较好找的，因为只要找一根线塞进去就可以了。然后从0到1半开半闭区间这个的平方到0到1半开半闭区间，这个是我想了一阵子，然后的话就是说你给任取这个平方的这个集合里面的两个数，哪个数对出来，一个叫 A 一个叫 B 的话，把它们用小数表示 0.A1 A2 A3， 然后是 0.B1 B2 B3， 然后它们的出来的函数值就是把这两个数相当于穿插起来，然后这样的组合的话，你得到任何一个小数，你通过把它们的第一位、第三位、第5位、第2位、第4位、第6位这样子把它再重新拆分出来的两个数字，一定是唯一的，所以是它应该也是一个单设。然后两边都找到了单设之后，这两个集合就是 of cardinality equal to。
So far so good. Okay, good. Thank you. All right. Now let's go to the last part, which is also quite interesting. So here we finally begin to see non-countable sets. So here we are asking you to show that the power set, which is a set of all subsets of the natural numbers, has the same cardinality as a set of real numbers. So remember, the set of real numbers is uncountable. Okay. So let's remind ourselves what a power set or the set of all subsets is. So for example, the power set of the set, let's say A comma B, is the set which includes within it the set with just single elements, with both elements, and also the empty set, right? So the set of subsets of A and B, there are two elements here. So the set of subsets of A and B are the set with only A, the set with only B, the set with both A and B, and the set with nothing in it, right? Similarly, if you have a set with 3 elements, then it will have 8 elements within it, right? Because all possible combinations, so in general, if you have a set with n elements, then there are 2 to the n elements within the power set, right? So this is the set and this is the power set. Now what happens if the set itself is countable? So for example, if the set is a set of natural numbers, then the power set, well, it's a set of all subsets of natural numbers. So those subsets may be finite, may be countable, right? And how many such subsets are there? And here this question is asking you to prove that there's actually an uncountable number of them. Okay, so it's really asking you to show a bijection between the power sets, between the power set of natural numbers and the set of real numbers, right? So in this case, Vejia had a nice solution. So here's one way of thinking about it. So let's go look at his solution. Okay, let's just do it on the sheet here. Okay, so given so what do we need to do now? Given this power set over here, so given any element over here, we need to show that it can be mapped to a corresponding element of a real number. So it can be mapped to the real line, and given anything on the real line, we need to show that it can be mapped to a power set, like an element of the power set here. Okay, so what's the trick? So for example, let's think about let me just do this differently. So we have the set of integers over here, a set of natural numbers. So natural numbers start from 1. So 1, 2, 3, 4, dot dot dot, n dot dot dot, something like this. And element from the power set is some subset over here, right? So there'll be some elements over here. A real number, so given any real number, so for example, suppose someone gives us the real number 0.A1, A2, A3, A4, let's just write this real number in binary format. So let's write it as 0.a1 prime, a2 prime, a3 prime, a4 prime, dot, 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 where each of these elements are either 0 or 1. Okay. So all this is saying is, let's write any real number in binary format. Okay. So now once we write this real number in binary format, so it'll look like something like, just for example, it'll look like 0, 1, 0, 1, 1, 0, 0, 1, 0, and so on, right? So that means 0 in the first location, 1 in the second location, 0 in the third location, 1 in the fourth location, and so on, right? So if we think about that, then given any real number like x, which is a real number, given any positive real number over here, we can, or given any x which is currently within the line 0 to 1, which is within this, or let's view this open set over here, within the open set 0 to 1, we can write it in binary format, and then given that binary format, we can then identify a set which comprises of, in this example over here, 2, 4, 5, 6, 7, 8, dot, 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 right? Wherever there are ones in the binary expansion of this real number, we will put those elements within that set, right? So given any real number, we will have identified a particular subset of natural numbers over there, right? And if you want to do the opposite direction, so that is to say, given any subset over here, given any subset of natural number over here, identify a real number from 0 to 1, well, what can you do? You can just take, for example, so suppose someone gives us a subset, 3, 5, 11, 17, dot, 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 something like this, right? So you can just identify a real number corresponding to 2 to the minus 3 plus 2 to the minus 5 plus 2 to the minus 11 plus 2 to the minus 17 plus dot, 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 right? And if you think about this, this will be a real number which will be between 0 and 1, right? So this, and given a different subset, you'll have a different real number. So again, it's a one-to-one mapping, right? So in this way of looking at things, we have now found one-to-one mappings from the subset of, from any given subset of natural numbers to the real numbers, and from any real number to a certain subset of the natural numbers. That must mean that the power set is the power set of the natural numbers. It has the same cardinality, has the same quote-unquote size as the set of all possible real numbers. In this case, the set of real numbers in the line 0 to 1. But we've already noticed that the line segment from 0 to 1 has the same cardinality as the positive real axis, and then it's a simple exercise to show that the positive real axis has the same cardinality as the full real axis, right? Which I'll let you think about how you would prove something like that. Okay, so that's what I meant by the missing steps in your proof, like just those two small other things over there, right? Okay, so could you try to explain this proof here?
这里教授还是讲了一个单设的问题，就是用这个二进制的表示方法去表示数，然后你给任何一个这种自然数集的子集，你都可以把它放到，比如说给了3、5、11，那你最后映射出来的数就是2的负3加2的负5这样子，所以是一定是单设的，就是这个是比较难想的吧。
Okay, so that's I think so Tian, is that okay?
他其实说了，就是说他从实数集构造了一个单设到这个 power set 里面，然后同时又从 power set 里面构造了一个单设到实数集里面。然后具体是怎么做的呢？首先实数集是这样的，这样它因为实数集的 cardinality 跟0到1之间的这个区间的 cardinality 是一样的，所以它直接构造是从0到1区间构造一个单设到这个 power set 里面。它具体做法是，首先每一个从0到1之间的实数都可以写成一个小数的形式 0.A1、A2、A 到 A4。然后呢，这个小数形式可以是2进制的，也可以是10进制的但是它没有什么区别。如果是写成2进制的话，那它每一位数就是0或者1，然后我们把每一位数当做是这个 是否在自然数里面选这个数的一个 indicator， 就是说，如果它是第一位是1的话，就说明第一个数被选中了。那如果第二位是0的话，就说明第二个数没有被选中。这样的话，这么一个0.1010这么一个二进制的一个小数，就对应于一个是否就是一个这样的一个每一个自然数是否被选中的这么一个模式。这个模式也就对应着自然数的一个对一个子集。对，所以这样就构造出了其中一个单设。那么另外一个单设怎么构造呢？就是说我给定一个自然数的子集，然后我把它们每一个自然数2就用这个2的 power 就是负这个自然数的这么一个对应出这么一个数，然后把它们全加起来，可以证明这个加法虽然它有无穷个元数，但是加起来是这个是收敛的，而且收敛到0到1之间的一个实数。这样的话，它就构造出了一个自然数的子集到0到1之间实数的这么一个单设。这样的话，它就证明了0到1之间这个 interval 和自然数的所有的子集之间，就 power set 之间的 cardinality 是一样的，就结束了。
Did he do a good job? Yeah. Okay, he did a good job. Okay, thank you to Vedya. I should also point out he posted a lot of solutions yesterday, and I'm sure we're all very grateful for his efforts over the semester. Okay, now there were a lot of solutions, lots of questions for this worksheet, and we're already half an hour in. We won't have time to discuss them all clearly. I'll try to do one more today at least, maybe 2 more. Let's see. Let me just point out the status of other questions. So question 2, this is a cute question. I don't think it's a very hard question. So between Franklin and who else? Rui Charles, we have a bunch of solutions. So I'm not going to discuss this. I think the solution is already fairly well written over here, so it's reasonable. Question number 3, Martin over here gave a nice solution. So question number 3 was asking you to prove. So for example, to formally prove that n+1 over 2n+1 converges to a half, and using epsilon delta notation, he's able to show that. So that's fine. The slightly more complicated part, probably the most complicated part, which is very nicely written, is to show that if 2 sequences converge, then the sequence which is the element-wise product of those 2 sequences also converges. So there's a lot of epsilons and notation here, but really I don't think it's very complicated. I think it may be valuable because not everyone may be comfortable with understanding epsilon delta notation. It may be valuable for, so well, let's see. Martin, could you just stand up for a bit? Is it possible for you to record a short video and describe part B like later offline? Okay, thank you. Because again, I think it's valuable for people to at least see how these proofs work. And again, like having at least one description in Chinese would be valuable for the class. So he's done an excellent job, I think, with part B. Well, with the whole question. So let's just leave it there, and he'll have a nice solution for you posted. Okay. Question number 4 asked you to look at the Cauchy convergence criterion. So the Cauchy convergence criterion again is a very useful way of checking when a sequence converges, even if you don't know what it converges to, right? So imagine that you had not studied calculus in secondary school and you did not know that this sequence over here, basically summation of 1 over k factorial, that this converges to E, Euler's constant, right? So you guys have studied calculus, you know it converges to E, but it's still a little bit mysterious, right? And if you had not studied that, you would not know that. So how would you check that this converges if you don't even know what limit to substitute over there? So Cauchy's convergence criterion gives us a useful way of checking this. And over here, Leithian has a nice solution. So first, but before that, let me highlight an interesting mistake here. Again, we also always learn by mistakes. So let me also point that out. And actually, Leithian, it's an interesting subtle mistake. Could I ask for your help here in helping explain this? So, so her first attempt was to show, okay, So I look at the mth term and the nth term, and look, Sm minus Sn can be m minus n over n factorial. So I can always make this smaller than any epsilon I want, just by choosing n to be capital N to be sufficiently large, right? And this is always a temptation. The temptation is to say, oh, I just want to make something sufficiently small, like smaller than any epsilon I want, and my proof is complete. But the tricky part is to show that once you've chosen your n, so this n you should really think of as depending only on epsilon, okay? So once you've chosen your epsilon, then you choose your n as a function of that capital N as a function of that epsilon, and this capital N should work for every small m and small n which are larger than that capital N, right? Okay, so let me just say that again. So the point is, first you choose your epsilon. Your epsilon is how close you want your sequence to be to the limit. You don't know what the limit is, but you want the sequence to be epsilon close to the limit. Given that epsilon, you then choose a capital N. So capital N is saying how far to the right on the integer line do you want to go? Like how far into the sequence do you want to go? Okay, and this choice can only depend on epsilon, nothing else. Now once you fix this capital N, then for every pair of integers larger than this capital N, your choice should work, right? And in her choice, that does not work because once you fixed the capital N, you can choose small m and small n such that small m minus small n can be larger than n factorial. Like the difference between this can be larger than n factorial. So it will become larger than your demanded epsilon, right? So this order of the quantifiers, the order in which you choose elements, is important. It's a subtle point and it's important. So that's what I wanted to highlight. Yeah.
这个数的确定顺序其实是就先有 epsilon， 然后我们再对这个给定的去取一个大 n， 就是一旦有就取定之后就不能改。那在取定的时候就因为那个小 m 和小 n 是肯定是大于那个大 n 的，但是小 m 和小 n 是可以任取的，所以在这种情况下就可以取到，就是在大 n 确定之后 m 减 n 就可以变得比较大，然后就会超过那个就是我们当时想放松的那个值，所以就不可以这样取，因为它有这样一个顺序在里面。
The TA wants something to add?
I need to compliment something. 他说的实际上是一个解题的 philosophy 的问题，就是不是 philosophy， 这太大了。Can you scroll down, scroll up a little bit？ 就从这个题里面看，它首先是说我去先做差 Sm and Sn， 它们的差是小于这个数，然后呢就小于这个数，然后当 n 很大的时候，这个对于固定的小 m 和小 n 这个数都一定会小于某个 epsilon， 也就是说它是先给定了小 m 和小 n， 然后再取大 n 的。那这个方法为什么错呢？因为can scroll down a little bit， 就是因为在证明 Kersey sequence 的时候，我们需要先就是说对于任意的 epsilon 误差项，我们要证明在这个序列到了某一个值之后。任何两个在这个值之后的两个数，它们之间的差是小于这个误差项的。所以说，在这个逻辑里面，你是需要先给定了 n 大 n， 然后你要证明在这个大 n 之后的任意两个数，它的差都小于某一个误差项。所以这么放缩的问题就在于，如果我们给定了 epsilon， 然后我们给定任意给定的 n， 然后我们总能找到两个数，总能找到一个小 m 和小 n 使得这个放缩之后的结果大于 epsilon。所以这个放缩是失败的，但是本质上它没有证明说没有说这个序列不是 Kersey sequence， 而是这个放缩放得太大了，就需要找到一个更精确的一个 bound 来去证明它是 Kersey sequence。
Did he do a good job? Okay, good. All right. So then let's see how to fix it. So in this case, the trick was to notice that if you have something like 1 over k factorial, summation 1 over k factorial, 1 over k factorial is always less than 1 over 2 to the k minus 1. So, and she justified it as over here. So because of that, then you can take the geometric series, you can add it up, and you can come up with the upper bound on the summation 1 over k factorial as 1 over 2 to the n minus 2, and therefore you can come up with a bound, right? So this is a very nice little trick, and because of this, then the whole thing works. Okay, so I just wanted to highlight the fact, because the order of the quantifiers is indeed important, and I just wanted to highlight that. Okay, thank you, Lathian. Good job. All right. So there's maybe time for one more question. Let's try it. This is an interesting question. I really like it. Maybe my favorite question of this worksheet. So this one is to show, is to examine the well, the Bolzano-Weierstrass theorem, but also dense subsets. It's a whole bunch. There's a whole bunch of interesting ideas here that are worth unpacking. Okay. So the first part of the question is maybe the least interesting part, actually. But anyway, so the first part of the question asks you to write the nth term in the sequence as a function of n, right? And there are multiple solutions over here. I'm not going to highlight them. There are different ways of writing them, and I'm not going to highlight them. They're okay, right? They're correct. Let's go to the more interesting parts of this question, which asks, is this sequence convergent? And if you think about it, well, it's not clear. So checking for convergence can be tricky. So usually the way to show that it would not be convergent is to show that, like one way of trying to show that it's not going to be convergent is to show that there'll always be, no matter how large a n you choose, there'll always be elements after that n such that the difference between Sm and Sn for something larger than some capital N will always be larger than some fixed amount. Okay, so if you think about it, there's a subsequence here like 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. This subsequence is converging to 0, right? And on the other hand, there's a subsequence which is like 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6. This subsequence is converging to 1, right? So if you think about it, in this case, you can, if you look at these two subsequences, let me write them down so you can see it. So there's a subsequence corresponding to 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, dot, 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 which is converging using the usual techniques that you've studied to 0. There's another subsequence which is like this, 3 over 4, 4 over 5, and so on. This is converging to 1, right? So that means if you wanted to show that the sequence was converging, so let's do a proof by contradiction. If you wanted to show that the sequence was converging, you would say that that there exists some sufficiently large capital N. So first of all, so for any epsilon greater than 0, there exists some capital N which is a function only of epsilon, such that Sm minus Sn is less than epsilon for all m comma n bigger than this capital N as a function of epsilon, right? This is the Cauchy convergence criterion. This is what you would write down. So let's prove a contradiction. Okay, how? By choosing, for example, epsilon to be 1/3. Let's choose epsilon to be 1/3, and now notice that there will be terms, like if we go sufficiently far over here, there'll be terms like 1 over 7, 1 over 8, and there'll be terms over here like 7 over 8, 8 over 9, and so on, such that when we look at the differences between these differences will be larger than 1 over 3. So for this specific epsilon, which is greater than 0, there is no sufficiently large capital N. There is no sufficiently large capital N such that all small m comma small n pairs the absolute value of that difference can be made to be less than 1/3 for all those pairs, right? Because there'll always be some pairs which are in which the first element is close to 0, the second element is close to 1. So I'm going to skip the arithmetic, right? It's basically algebra, but you can show that it cannot be convergent because there's a subsequence converging to 0, there's a subsequence converging to 1. So therefore, you cannot have Sm minus Sn converging to 0, right? Okay, so it's not converging. In fact, just by what we already discussed, we can show that the supremum is 1, the infimum is 0. So why is the supremum 1? Well, if you look at all the elements in this set over here, the numerator is always less than the denominator. So the supremum cannot be larger than 1, right? But there is a convergent subsequence which is converging to 1, and therefore the supremum, which is the least upper bound, is 1. It is the smallest number which is it is the smallest number which is larger than everything else within the set over here, right? Similarly, the infimum is 0. The infimum is 0 because the numerator is always greater than 0, and therefore it is the least it is the largest lower bound. So you have something like that. Okay, the Bolzano-Weierstrass theorem. So the Bolzano-Weierstrass theorem, if you remember, it basically says that every bounded sequence has at least one convergent subsequence, right? So over here, this is bounded because everything in this set is no larger than 1, is no smaller than 0, and therefore it's bounded, right? And therefore there must be at least one convergent subsequence. And if you look at the solutions posted over here, they pointed out, well, for example, there's something converging to 0, there's also something converging to 1. Now, what's the maybe the most interesting part of this question is the last part, which is asking you to find the set of limit points to this sequence. So a limit point to a sequence is a point such that you can find a subsequence within the sequence such that it converges to that limit point. So let me say that again. So suppose someone gives us a sequence over here like S1, S2, S3, dot, 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 Sn, dot, dot, dot. If I can find a subsequence such that the subsequence, maybe S2, S5, S7, dot, 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 converges to some limit point L, then this L will be a limit point. Now we've already identified that this sequence has both 0 and 1 as limit points, right? So it's certainly possible for the set to have more than one limit point. So sorry, for the sequence to have more than one limit point, right? But what's really interesting about this particular sequence is that every number from 0 to 1, every real number from 0 to 1 is a limit point of the sequence. Okay, every real number is a limit point of the sequence. Why is that? Because you can, so suppose you had a rational number. So let's okay, I'm going to go 2 minutes over class time. I apologize. Okay, just 2 minutes. So let's look at two cases. So suppose your number was of the form p over q, then you have p over q, 2p over 2q, 3p over 3q, and so on. So you'll have an infinite sequence which takes a value p over q, right? So you'll certainly, so p over q, if p is less than q, will always be a limit point of the sequence. Okay, so any rational number between 0 and 1 is a limit point. If you have an irrational number, so suppose you have 0.31 or I don't know, something like 1 over square root 2, which is like 0.707 dot dot dot, something like that, right? So how do you approach this? Well, you take 0.7, then you take 0.70, then you take 0.707, then you take 0.70 dot dot dot, right? So each of these is a rational number. This is 7 over 10, this is 70 over 100, this is 707 over 1000, and as you can see, this subsequence over here is going to converge to your irrational number, and this subsequence will be an element of the will be a subsequence of that full sequence, right? So this is showing that this sequence within it contains subsequences converging to any real number, right? Which is very strange. The set of real numbers is uncountable. This sequence is countable, but the set of limit points of this sequence is uncountable, right? So even a smaller infinity can contain within it a larger infinity, right? In a certain sense, which I find quite beautiful. So these sets are called dense sets, and there are many other beautiful things about sets like this. So anyway, that's it for today. We've covered the first 5 questions. Now, there's still, let me just highlight a couple of things. There's still many other questions to be discussed. There have been solutions posted to many of them, but not all of them. So especially things where I have not yet marked things like this is a good note. There are still potentials for posting solutions there. And because, you know, I understand there's a lot of material to cover here. So tomorrow, after the tutor does a review, we'll try to answer some more questions, just so you have a chance to understand this exercise sheet more deeply, right? I think there are interesting and important ideas here that still should be discussed. So I'll help lead that discussion tomorrow as well. Okay. All right. Class is over. Please do give us your comments. Last week of classes. So thank you for paying attention.